Hello, I'm sorry. Yesterday I missed the first few minutes in my recordings, and so I redo it now. And thank you again for to the fellow who advised me to start the recording. So I saved most of the lecture of yesterday. So uh, we started with solving the two exercises I had left for the week. And the first one was they are very different in character. The first one is this: the K cube is the graph whose vertices are the order k tuples of zeros and ones, two vertices being joined if and only if they differ in exactly one coordinate. Okay, so this is the description that we can also draw somehow, at least for the first few cases. This is one cube, so one tuples of 0 and 1, and they differ by one coordinate, so we join these two vertices by an edge. The two cube, so tuples, pairs of zeros and ones, 0, 0, 1, 0, differ by just one coordinate, and so they are joined by an edge. 0, 0, and 1, 1 do not differ by just one coordinate, okay? And so they are not connected by an edge, and so on and so forth. And we also have a rather simple drawing of the 3 cube, okay? And so again, we see 0, 0, 0, 1, 0, 0. They differ by just one coordinate, and so they are joined by a link. 0, 0, 0, 1, 0, 1 do not. They are not joined. 0, 0, 0, 1, 1, 0 are not do not differ by just one coordinate. They differ by more than one coordinate, so they are not joined by an edge. 0, 0, 0, 0, 0, 1 are. 0, 1, 0, 0, and 0, 1, 0 are joined because of the rule we have assumed. Okay. The book asks for some proofs. Forget about these two, but what I'm interested in is that you should show that any such K cube is bipartite. So we can, of course, take inspiration by the easy low K cases, okay? And so we can see here that we can put 0 in one part of the bipartition, 1 in the other part. Oh, please do remember the correct definition of bipartite. The correct definition of bipartite graph is that you can subdivide the vertex set into two sets whose union covers all the vertex set and which are mutually disjoint, no element in common, so that, and this is the important part, so that each edge of the graph joins a vertex in one with a vertex in the other parts of the partition, okay? So we can have X and Y, say, the two sets into which we make the bipartition, and each edge must connect an edge in vertex in X with one vertex in Y. And so red and green here are X and Y, and actually here we can see that I can divide the vertices of this graph into red and green so that each edge connects a green with the red. Same thing for the 3 cube, okay? And now we should devise something which is valid for any k, meaning k equal 1000, okay? It's no use doing the 4 k's and stop it, okay? It's no use of make an example. With examples, we may envisage a general rule for showing that that any k cube is actually bipartite. So what should we do? Give a general rule for saying if we are in the k cube, I shall put in set X all vertices which are such and such, and in the Y set all other vertices which are in that different condition. Okay, and of course you can look at what we have done in the small cases and try to generalize the rule. Okay, and a fellow in class gave the only solution I know, which is on the parity of these k tuples, okay, and which can be used for any k, meaning we can put in X whatever the length of our k tuples is. We can put in X all k tuples whose number of ones is even, as we did here and as we did here. And in Y, all k tuples whose number of ones is odd. Okay. Remember that 0 is even because you can divide it by 2, meaning it is a multiple of 2. 0 is 2 multiplied by 0, so it is a multiple of 2. Even for an integer means multiple of 2. So 0 is even. Okay, so what you get is something which generalizes what we have done here and is possible to be defined with any k. I give you k equal 1000. Okay, you take the 1000, the 1000 poles of zeros and ones. The ones which have an even number of ones are in X. The ones which have an odd number of ones are in Y, and then how can I be sure that this is a correct bipartition? Well, what do edges in a K cube join? They join two K tuples which differ by just one coordinate. So what does that mean? That given any edge, one of the ends, one of the two vertices it joins together, one of the ends has in a certain position, say position I, it has 0, and the other end in exactly the same position I has 1. And for all positions which are from 1 to k except I, they have exactly the same numbers. Okay, so naturally, if the one k tuple that edge is incident on has a 0 and the other has a 1, then necessarily the parity of ones is different in the two k tuples. Okay, assume that the one which has 0 is in X, then necessarily the one which has 1 is in Y. Or if the one which has 0 in position I is in Y, necessarily the one which has a 1 in position I is in X. Okay, so for instance, in this case, we can pick up this edge and does it do its work well? Sure, because these two triples differ just by the first coordinate. So here k equals 3, I equals 1, and what do we have? We have that this triple belongs to y, and this triple having one more 1, here it was not the number of ones. Here necessarily it becomes an even number of ones, and so it belongs to X. Okay. Instead, if I pick up say these two, this edge, then what do we have? We still have k equal to 3, of course, and then we have that the position where the two triples differ is position I equal 2. In position 1, they are equal. In position 3, they are equal. In position 2, they differ by that coordinate. And what we have here is that here we have an odd number of ones. So this vertex belongs to y, and this has one, sorry for the sort of pun, we have one less. We have one position less where we have 1, and so the number of ones becomes even, okay? And so necessarily this edge joins a vertex in y with a vertex in x. But this is not only for these little k's, it is true for any k. What I'm insisting on is this is a particular type of mathematics because it works with finite things. This is finite, these are finite, even the k cube is finite, but you must be able to reason with generality with any k, not just k equal 1, 2, or 3, or 1000, but any k. So be able to make an argument which is valid for infinitely many k, where for each k you have a finite thing. Okay? Another simple to state, more difficult to deal with exercise was this. It should come. Oh no, sorry. Oh, it was here. Find a non-trivial simple graph whose automorphism group is the identity. Let's see at each of these words. Never, please never state something if you do not know the exact meaning of all words, all symbols you are using. I prefer that you do not say something rather than saying something of which you do not know the meaning. Okay, so find the non-trivial. Non-trivial means at least two vertices. Simple graph. Simple means no multiple edges, no loops. Whose automorphism group, what is the automorphism group? It is the set which actually is a group because we have a binary operation composition which gives a very good structure to this set, a structure of group, but we are interested in the set in this moment. The set of automorphisms. What is the set of automorphisms? Of those isomorphisms of the graph to itself. Sorry. We have seen in the previous lecture a graph with 6 automorphisms and another graph with 2 automorphisms, that is self-isomorphisms, isomorphisms of the graph to itself. Okay? So please go to the previous lecture to see those examples. And what is asked for here is that this graph has only the identity as automorphism. What is the identity? It is the most simple automorphism, which is always there for any graph, sending each vertex to itself, each edge to itself. This trivially enjoys all the properties for an isomorphism. And so it is an isomorphism of the graph to itself, so it is an automorphism. And you never can get rid of that automorphism. But what is asked for here is to find a non-trivial simple graph which has no symmetry, because automorphisms mean some symmetry in the graph, and we have seen the one with 6, which was highly symmetric, the one with 2, which was symmetric, but in a less conspicuous way. Here we want a graph which has no symmetries, no automorphisms, beyond the one which is unavoidable, the identity. We have a solution given by the Turkish lady in class, which is this, and which is very nice, and it is the simplest possible. Let's see why it has only the identity as automorphism. Please remember this notion of degree, which we are going to see formally in the second part of this lecture. And which is simply for each vertex the number of edges adjacent to it, okay? And this fact is very important and was remarked by one of you, and it is that if you have an isomorphism between two graphs, then a vertex in the first graph with degree k must be sent to a vertex in the second graph with exactly the same degree k. Okay, so the degree we in slang we say that isomorphisms preserve degree, meaning this. It transforms a vertex of degree k into a vertex of the same degree k. Okay, so let's look. We have 3 vertices of degree 1, so in principle it might be possible to send this one to this one. Let's see why it is not possible. It all comes from this vertex, which is the only one of degree 3, and so it has to be sent to itself by an automorphism. So surely this for this vertex we have a necessary image, which is itself. Okay. Once we know this, then this propagates, so to say, to the other vertices. For instance, this. This is one of the 3 vertices of degree 1, okay? But it is the only one of the 3 which is adjacent to the one vertex of degree 3, okay? And adjacency is preserved by isomorphisms. Look back to what is an isomorphism and what is not. I also have given grace to some suggestions by some of the students outside of the class. Some examples of non-isomorphisms. Look at those which are very interesting. Okay, here we must have that if a vertex of degree 1 is adjacent to a vertex of degree 3, then the corresponding vertex of the one of degree 1 must be adjacent to the corresponding one of the vertex of degree 3. Okay, we have seen that since the vertex of degree 3 is the only one present here, it must be transformed into itself. But this means that also this must be transformed into itself. Why? Because of the 3 vertices of degree 3 or degree 1, sorry, it is the only one directly joined to the vertex of degree 3. So this cannot go to this or to this. It must be transformed to itself. Not in a very different way, we can look at other vertices. For instance, we have 3 vertices of degree 2. Okay, so what? Can this vertex of degree 2 be transformed into this? No. Why? Because it is adjacent to a vertex of degree 0. And also this is, but it is adjacent to a vertex of degree 3, and this is not. It is adjacent to a vertex of degree 1, sorry, this is of degree 1. It is adjacent to a vertex of degree 1, and this is adjacent to a vertex of degree 1. But this is adjacent to a vertex of degree 2, and this is adjacent to a vertex of degree 3. So this cannot be transformed to this. Can this be transformed to this vertex of degree 2 as much as this? No. Why? Because it's true that both are adjacent to the vertex of degree 3, but this is adjacent to a vertex of degree 1, and this is adjacent to a vertex of degree 2. So this cannot be transformed into this. It must be transformed to itself. And so this must be transformed to itself by the same reason, because it is adjacent to this, which has to be transformed to itself, and this must be transformed to itself, this to itself, this to itself, just by reasoning on degrees. I'm sorry if I have said wrongly 0 instead of 1. Degree 1, degree 1, degree 1, okay? Sorry. I don't want to repeat the recording, please correct. Okay. Is that clear? So, again, thanks to the Turkish lady here in the classroom. And we have this very interesting object. Why? Because if you have tried, and I hope you have tried for 5, 10 minutes, you probably have found some objects which were with some symmetry beyond the only one which is requested here. Okay? No, all right. I hope this is clear. Anyway, you can always write to me for more explanations, for clarifying what I have said. Okay, so now I stop because the rest of the lecture is normally recorded.